Hello everybody. Today I am going to talk about special relativity again. My first video on this channel was about special relativity, about Lorentz transformation. And before that there was Galileo transformation, but whatever. Today I'm going to talk about time dilation. In my first video I said that the Lorentz transformation, Einstein made it, but I guess it wasn't. Lorentz made it. A person called Lorentz made it. He was a scientist that maybe not experimented, but made theories about electrons and those stuff. And now, what Einstein did was this. This is a famous diagram thingy of how special relativity works. This drawing, there's a box, and this box has a mirror and a laser at the bottom. Now you shoot light into that laser, and it comes back because it's a mirror. And this box thingy moves at very high speed. So when it moves, here's one box, another box, and another box. Well, what I've drawn here isn't three boxes. They're supposed to be same. This thing is moving, and this is different time states. So now, to a moving person, it would look like this. But to a stationary person, relatively moving to this box, or the person that is moving with the box, it would look something like this. And this is the thing that the moving person will see. For simplicity, let's say the moving person is in a rocket, a glass rocket, so you can see the inside, and holding this thing. Actually, if it's in a rocket, you don't have to hold it. It's stationary stationary relative to the rocket. Now we're gonna call this line L, and this line H. H, because, well, yeah, the height of the box. And this bottom part of the two triangles, or bottom part of the big triangle, we will call it VT. If you didn't see that video, my first video, basically L is, well, I didn't use L then, but H is for height, L is for length here, and this thing, it's velocity multiplied by time. So, and well, this equals distance, so the distance it has moved. And also C is for light speed. C is for the speed of light. Also, there's a thing called gamma, and gamma is called gamma is root square of 1 minus v squared over c squared, and 1 over it. And yeah, that's gamma. And what I showed you in that video was about length contraction, which is x prime. The prime means it's in the moving perspective. The moving perspective's space is gamma times x. There's no prime here on this x. That means this is a stationary person's perspective. and x minus vt. And as I said, vt is velocity times time. Velocity is v and t is time, so these two multiply. This v is for the moving perspectives space. And so basically this gamma, if the velocity increases, this downside part of this thingy, the downside part of gamma is getting, well, smaller, which makes the total bigger. It makes gamma a lot bigger. And when v equals c, that would mean gamma is equal to infinity. So yeah, it changes around and stuff. Length, you should just watch that video if you're interested in the length contraction part. And now over to this part, and what Einstein did. Well, Einstein imagined a box that is moving like this, and he shot a light through, and it made this shape, and this is Vt. And now half of it would be Vt over 2, Vt divided by 2. And now, so using the Pythagorean theorem, well, this is of course a 90-degree angle, and so using the Pythagorean theorem, L squared is equal to h squared plus 4, v squared t squared over 4, because this squared is that, this squared is that, this squared is that, and because this is a 90-degree angle, this makes sense because of the Pythagorean theorem. And now also we're going to call the moving perspective's time t prime. So t prime would equal t prime would equal yes, t prime, wait, let's write the prime over here. T prime would equal this because, well, the laser beam is moving at, well, light speed because it's light. Because time is equal to distance divided by velocity, the distance is 2 times h because, well, the light went this much up and down. So 2h divided by c because light speed. And yeah, so you get that. And for the L, which is the distance that the light moved for the stationary person, we're just gonna call it t. And oh wait, that's a prime. We're just gonna call it t, and t would equal 2 times, it's basically same as this thing, 2 times 2L divided by C. And we're trying to get what L squared is and what H squared is. So now we move this C into here and 2 into here, so well, multiply C to the T and then divide CT by 2. So L would equal CT over 2, and then H would equal the same way. H would equal ct prime over, this would equal ct prime over 2, like that. And so now we write this thingy down using this. So L squared would be, this would be c squared t squared over 4. This equals, I'm going to erase this, and this equals c squared t prime squared over 4 plus, well, this thingy. And yeah, so we multiply 4 to both sides of the equation, so we get the c squared t squared equals c squared t prime squared plus v squared t squared. And we move this to over here by contracting this v squared t squared from both sides, and now we get c squared t squared minus v squared t squared equals c squared t prime squared. And now we can do something like this. We get these two and pull it out. So t squared multiplied by c squared minus v squared would equal c squared multiplied by t prime squared. And we divide this thing by this thing. So we would get, I'm going to write it over here, t squared equals c squared over c squared minus v squared multiplied by this whole thing multiplied by t prime squared. We divide the c squares by c squared. We divide both the top and the bottom of this c squared over c squared minus v squared. So that becomes 1 and c squared, like that. We divide it by c squared and this happens. So we can see that t squared is equal to 1 over 1 minus v squared over c squared multiplied by t prime squared. And because this is all squared, these two are squared, so we put a square root down on this one. Well, basically we use a square root on everything, but these are squares, so this becomes a square rooted one. And if you try to put a square root on 1, it doesn't work, so we just have to put it down on the bottom part of the thingy. T would equal the thingy and multiply by t prime. So you can see it's gamma, it's the same thing, it's gamma t prime. So now what happens is, well, as I said, as the speed increases, the Lorentz factor gamma also increases. And when the v equals c, gamma equals infinity. Yeah, so because Wait, before that, we can also write the equation down as t prime would equal t multiplied by this, the Lorentz factor. And, well, this whole thing increases if the v increases, but this thing decreases if the v increases because it's 1 minus v squared over c squared. If the v increases, it's gonna contract more from 1, and that would make the whole thingy decrease. So you can see if the v increases, t multiplied by gamma decreases, and that would make the time of the moving perspective also get contracted. Time dilation. So let's say the t is 1. A second has passed for the stationary perspective, and then the moving perspective is moving at a great speed. If it's moving at a great speed, it is going to make 1 multiplied by this decrease, and that will make the time for the moving perspective 1 second has not passed yet. A smaller amount of time has passed for the moving perspective, and that would mean the time is getting dilated for the moving perspective. And I think that's all about how Einstein thought about this special relativity thingy. And I think this is all, and I hope you enjoyed. Thanks for watching. And also, I learned this thingy from a cool science stream, and I will leave a link down below. And thanks for watching. Bye.